Hello everyone, uh, welcome back again. In this lecture, we'll begin discussion on wave equations in higher dimensions. So in the next few classes, this will be the main discussion, and also discussion will be mainly on uh, the initial value problem. Okay, so let me again state it. So this is the wave equation in uh, higher dimensions. So again, a second order equation. So utt minus c square Laplacian u equal to 0 for x in Rn and t positive, and at t equal to 0 in that space, that is x space. So we provide the initial conditions. So that's the initial position and initial velocity. So this equation also arises in many physical processes. So as we go on, we'll discuss some of them. And as usual, so this Laplacian, so sometimes to stress the dependence on the variable, we also write that as Laplacian sub x, and that is the second order operator Laplacian, and c is a given constant. Okay, so before we go further uh, in the discussion of this initial value problem, let's recall what we have done for the case n equal to 1. So that was in the first part of this course. So the important formula we derived for the D'Alembert's for the wave equation in one dimension, and that's D'Alembert's formula. So let me write it. Okay, so this is given by u of x t equal to half of phi of x plus ct plus phi of x minus ct plus 1 by 2c, this integral x minus ct to x plus ct psi y dy. Okay, so phi and psi, they come from the uh, initial conditions. Okay, so the one difference I would like to uh, remark here between this formula and the formula for the solution of the heat equation and also Poisson equation we have discussed is that, so any solution of this wave equation in one dimension satisfies this D'Alembert's formula, and conversely any function u defined by this D'Alembert's formula satisfy the wave equation with these initial conditions. Okay, so that's the difference. So there is, so any solution automatically satisfied this D'Alembert's formula, and that is not the case with, for example, heat equation. Though we derived the Fourier Poisson formula for a solution, but in general that is not the only solution. There we have seen that uniqueness is not there, but that is not the case with this wave equation, and there is uniqueness here. Okay, so at this stage I also want to uh, remark regarding a fundamental solution. So in the first part of this course and even in the second part, we have been talking of fundamental solutions for the Laplace operator and also heat operator, but we have never talked uh, a fundamental solution for the wave operator. It is not that the wave operator does not have a uh, fundamental solution. It has. Okay, in fact It's a celebrated theorem of Malgrange and Herem-Priest. So just let me state for the record, who states that every constant coefficient linear partial differential operator PDO L has a fundamental solution E. Okay. So the meaning of this statement is that this, when you operate E, when you operate the given partial differential operator on this fundamental solution, so that is L of E, we should get this delta function. And in the case of Laplace operator and also heat operator, we have seen in general uh, in general situation, this fundamental solution is not necessarily a function. Okay, so we have to enhance, we have to go outside the realm of functions. So in case of Laplace operator and heat operator, the fundamental solutions are C infinity function except a singularity at one point. Okay, but in general, this the fundamental solution given by this theorem need not be a function, and it's can be a distribution, and that's where the trouble starts. So we have not developed uh, any concept regarding distributions and their uh, operations, their algebra, their calculus. Okay, so that's very modern part of this subject, this PD subject. Okay, so that's why we are not discussed in detail about the fundamental solution of the wave operator. I just try to indicate what that is in case of n equal to 1. And more importantly, this Malgrange-Herem-Priest theorem, uh, depending on the nature of this fundamental solution, a new classification arose. Okay, and now we classify the linear class of linear partial differential operator of any order, not necessarily second order, of any order, uh, depending on the nature of this E. So they are now classified as hypoelliptic operators and non-hypoelliptic operators. So this Laplace and heat operator, they come in the class of hypoelliptic operators, and wave operator is a typical non-hypoelliptic operator. Okay, so let me just indicate what this fundamental solution for the wave equation in n equal to 1. Okay, and we try to write this D'Alembert's formula in terms of that fundamental solution. Okay, so for that purpose I define this. So it is fundamental solution of the wave operator, but again I will not go into the details how this comes uh, and how one has to do it in a general case. Okay, so that's just take this as a kind of ad hoc procedure. Okay, so define this function kw. It's a function of two variables x and t. For t positive, so that as a function of x is nothing but this 1 by 2c, so that constant comes. So this is the characteristic function of this closed interval minus ct to ct. So taking t positive and c the positive constant that appears in the wave equation. Okay, so characteristic function for a general subset is defined by chi a of x equal to 1 if x belongs to a and 0 if x does not belong to a. Okay, and now with this that w is for wave, so this characteristic function fundamental solution for the wave equation, and now you compute this convolution. Okay, so take any nice function psi, and you psi a function of x only, and you uh, compute this convolution, and that convolution by definition is given by this integral. But now that kw, okay, so just write that one more step here. So this kw x minus y, so kw x minus y t is 1 if minus ct is less than or equal to x minus y less than or equal to ct. Otherwise it is 0. Okay, so this integral uh, is restricted only to this interval minus et to plus ct, and then you make change of variable. Okay, so you are integrating with respect to y variable, so you make change of variable, and finally you arrive at uh, this integral. So integral 1 by 2 c, so that 1 by 2 c is factor in this fundamental solution, and that's 1 by 2 c to x minus ct to x plus ct. Okay, and that is precisely, if you look at the D'Alembert's formula, it appears here. Okay, so this part now equal to kw dot t star psi. So what about the first part? That first part, so again you take the convolution of kw with phi, so we get that. So just now we computed that convolution, so instead of psi we have taken of phi, and now you differentiate with respect to t. Okay, so if we differentiate this expression, you get precisely, so there is a c there, that c cancels here when you differentiate with respect to t, and you get half phi of x plus ct and plus phi of x minus ct, and that is the first part in the D'Alembert's form. Okay, so therefore we rewrite the D'Alembert's formula. Okay, just recall that. Okay, highlighted in. So in terms of this kw, okay, so that is d by dt of this convolution kw with respect to and the function phi, and then there is no differentiation, so only convolution with respect to the psi variable, and this is written as this d by dt of this, but this has to be interpreted in a suitable sense in distribution sense. Now this is just for the sake of information, so we are not going to develop distribution theory in this course, and so when we learn that distribution theory, so this turns out to be half uh, del, I will just write it here, plus ct minus ct. Okay, so this is Dirac delta function. So this is the reason we didn't have any discussion on the fundamental solution of the wave equation. Okay, because we have to develop these new tools and then the calculus uh, related to that. Okay, so that will be really an advanced course. Okay, what I would like to remark is, so this is what we derived for the case n equal to 1, D'Alembert's formula, and now we wrote that uh, in a different fashion using this fundamental solution. And this form, okay, this form of the solution is retained for all dimensions. So that's the important thing. So there will be a kW, okay, so that depends on the dimension. Okay, so and so we'll have one convolution here, and then we have to take the time derivative and we get another convolution there. So the solution even in any dimension is given by such a representation. So that's one important remark I want to make. And uh, yeah, this nature of this, though I am not explicitly stating that, but when you write the formula for the solution of the wave equation in higher dimensions, you will recognize the form of this fundamental solution, and that is very much dependent on uh, the dimension n, and in odd dimensions it will have uh, a particular qualitative property which is very different from uh, fundamental solution for even dimensions. And so even in one dimension, so you will see later that there is no resemblance of this fundamental solution in one dimension and higher dimensions. Okay, so now we are going to derive a formula for the solution of the wave equation in higher dimensions. Okay, so that's our next agenda. Okay, so unlike the case n equal to 1, we immediately do not have any idea how to proceed. So to get some ideas and motivation, so let's start with some simple solutions. Okay, so begin by looking at radial solutions. So if there are possibility of finding a radial solution to the wave equation. Okay, and this is certainly a possible way when the initial conditions phi and psi themselves are radial functions, and then in that case certainly we can look for a radial solution. So the this dependence on of u on x is only in the radial direction, so it's just a function of mod x, and in that case the Laplacian, we already seen this, so the Laplace operator in the, so this is r is equal to, that, so r is equal to mod x. Okay, so in this way we have reduced the given equation, given wave equation in n plus 1 variables into an equation which is 1 plus 1 variable. So this is essentially reducing to an equation in, so let me write that 1 plus 1 variable. So there is already a t variable, and now we have only the r variable. Okay. And if this factor were not there, it's simply wave equation in one dimensions. Okay. So in this presence of this a first order derivative with respect to r, it's no more an wave equation, but in some cases it can be reduced to one dimensional wave equation by some suitable transformation. So for a general n, we'll see later, but for the time being, just consider the case n equal to 3, and so this coefficient will be 2 by r. Okay. And this simple transformation, now you just put this v equal to ru, okay, and then use the Leibniz rule. So I want to compute the second derivative of v. Okay, so just use the Leibniz rule with respect to r. So there is no problem with t, because this is again multiplying by r. So t derivatives of v are same as t derivatives of u, just multiplied by r. Okay. So this del square v by del r square is equal to 2 del u by del r plus r del square u by del r square. Okay. And now when you substitute these computations here, you immediately see that v satisfies this first order. So this is wave equation in one. Okay. Now the variables are r and t. Okay. And so we can immediately use the D'Alembert's formula to write down the solution for this v. Okay, so obviously the initial conditions at t equal to 0 for u and u sub t are transformed to initial conditions on v. So using those initial conditions, we can immediately write down uh, the solution v, and once we know that solution v, so simply divide by r and we get uh, an expression for the solution of u in this particular case. Okay, and this gives us good motivation. So somehow bring in an extra variable r, okay, in which case the given wave equation is reduced to an equation in 1 plus 1 variables, and by suitable transformation eventually to 1D wave equation. Okay, so our next target is how to transform the given wave equation into a one-dimensional wave equation, because we know a lot about one-dimensional wave equation, and that will help us in deriving a formula for the solution even in higher dimensions. Okay, and such a procedure of transforming the given wave equation in n dimensions to an equation in just two variable is provided by this method of spherical means. Okay, so let me again recall what is spherical mean of a function. This we have seen in a lot in the study of Laplace equation and Poisson equation, and very fruitful one. and we will also see that it's also fruitful in dealing with this wave equation in multi dimensions. Okay, so let me just again recall that what is the mean value of a given function h. So h is a given function from Rn to R, a C2 function. So for the definition we don't need C2, but we want to do some computations, so that's where I need C2 function. So even continuity, just with continuity we can define the spherical mean function. Okay, so we denote the spherical mean function of h by mh. So it's a function of two variables x and r. Okay, so this is nothing but the mean value of the given function h over a sphere of radius r centered at x. Okay, so this is mean value of h over a sphere of radius r centered at x. And as we proceed further, it will be clear that, so this is the one new variable we are looking for. So this is just to begin with, it's a positive real number, so we'll soon extend it to all real numbers. So x essentially plays the role of a parameter. So in the discussion of the equation satisfied by this mh, x hardly plays any role, as we see further. Okay, and sigma n is the surface area of the unit sphere, and its numerical value is given by this number 2 pi to the n by 2 divided by gamma of n by 2, and gamma is the Euler gamma function. Okay, so in this definition, this mh is defined only for r positive, but by simple change of variable we'll immediately see that it's defined for all r. Okay, so you just change the variable here, so you put replace this y by x plus r xi, and xi varies over the unit sphere. Okay, and change of variable, this r to the n minus 1 just vanishes. Okay, in this form mth now is defined for all r. Okay, and by changing r to minus r, and then we can change the variable xi to minus xi, and this is a sphere, so there is no change there. So you immediately see that as a function of r, this mean value function mh is an even function. And the good thing about this mean values, so we can also recover the function we started with, namely h, by taking limit as r goes to 0. Okay, so these two properties just, so it's an even function of r, and we recover h by taking limit r equal to 0. Okay, so these two are important properties. Okay, and because this is an even function, so we'll also see that, so del by del r, so just work out it's 0 is h. So we are interested in finding the second derivative of this mean value function mh with respect to r. Okay, so that's what is, and we want to relate that how it is related to the second derivative of h. Okay, so we'll begin some computations. So if we use this form of the definition, then it's difficult to differentiate with respect to r, but this change of variable, now r has entered the integrand, so there is no r on the domain, so it's easy to uh, differentiate. So we just take the differentiation sign onto the integral sign, and so that's del by del r is equal to, so now r is here. Okay, so just take the del h by del I, and then when you differentiate this variable with respect to r, you get a chi. Okay, and that certainly we can write it as, so remember, so this j, the uh, variable with respect to which we are integrating. So just exercise some care there, and we want to apply the Green's formula. Okay, Green's formula. So let me again write it in the side here. So we have Laplacian u. So this is volume integral, and this is just grad u. So this is the normal derivative. So this is ds. Okay, and this is just nothing but grad u dot. And since this is the unit sphere, the unit normal is in the direction of j itself. Okay, so this is mu I in this case. So it's of this form, but only thing is you have worry about this r coming there. Okay, so this produces an extra r here. That's the only difference. And now this is volume integral. So this is surface integral. Okay, and using Green's formula, that we have converted into a volume integral. Okay, and now this, okay, there is r missing here. I'll write that. So this is r, and the variable of integration is j. So that's nothing to do with x. So you just bring this Laplacian operator outside the integral, and rest of the integral there. And again that you change the variable, so you just write that hy over surface x. This is surface integral. So let me okay, this is volume integral, no problem. And this volume integral using spherical coordinates, we just write it like this. Okay, and when you do that change of variable here, you get a factor of r to the n. There is already r there, so this is just 1 by r to the n minus 1. Okay, so now multiply both sides by this r to the n minus 1. So that's left hand side is already del by del r mhx r, and this one I want to write as this surface integral as mh x rho. The only thing is there is a factor 1 by rho to the n which is not there, so that's why you are multiplying by this extra rho to the n minus 1. Okay, And now you just simply differentiate one more time, so we get this, so that when you differentiate with respect to r, so it just comes out to be r to the n mhx r, and again this r and x is nothing, they are independent, so this Laplacian operator I can move anywhere. Okay, so this is the relation between this second derivative of the mean value spherical mean function with respect to r and the Laplacian of the given function h, and this is called Darboux equation, and we'll continue from here next time, and how this should be applied to the wave equation. So ultimately it's for the purpose of getting solution of the wave equation, and we will see how this Darboux equation is applied to the solution of the wave equation. Thank you.